Hello class, so this week's lecture is based on atmospheric moisture and we'll be covering topics of the three different phases of water and relative humidity as well as cloud development. So I first wanted to show a diagram of the water cycle. So I felt like this showed the phase changes of water very accurately. So first, let's start off with evaporation, and here you can see that the sun's energy, it warms up the body of water, and it transforms the liquid water into water vapor, and this process is called evaporation. And then the water vapor changes back into liquid, which is the process of condensation, and this is when cloud formation starts to occur. And as you can see here, as the cloud particles get larger, this is when precipitation occurs. I also like this diagram because it shows the other phases of water, sublimation and deposition. Sublimation occurs when the solid turns into vapor, and then deposition occurs when the water vapor transforms into solid. And as you can see here, it occurs on the snowy mountains. So for changes of state, I want to cover the three phases of water, which are solid, liquid, and vapor. So the transfer of energy between the water and the surrounding environment is referred to as latent heat. So latent heat is important because that's the energy that is required for the water to change, whether it's released or absorbed. So in this process, from ice to liquid, this is known as melting. From liquid to vapor, this is known as evaporation. And straight from ice to vapor, it's known as sublimation. And in this process, there is heat energy that is being taken away from the environment, meaning that this water molecule is absorbing the heat from the environment. So as it absorbs the heat, it is making the surrounding environment cooler. And in this stage right here, it's the opposite. From vapor to liquid, it's condensation, and liquid to ice, it is freezing. So, and again, deposition from vapor to ice. So in this process, heat energy is released to the environment, meaning that the water molecules are releasing the energy to the environment, the heat energy, so that's making the surrounding environment warmer, whereas the water molecules are staying cool and changing into a cooler form, which is ice. And I want to give one example of latent heat energy. So when you're holding a piece of ice in your hand, the ice is melting in your hand, and the reason it's melting is because it's taking the energy from your hand and it's absorbing the energy, causing the ice to melt. So in this case, your hand is the surrounding environment and the ice is absorbing the energy from it. So that's an example of latent heat energy. Next, I want to talk about water vapor. So there is a small percentage of water vapor in the air, in the atmosphere, but even though it's a small percentage, it's still an important gas because it tells us it's a good indicator of atmospheric processes in the atmosphere. So humidity is the amount of water vapor in the air. So an important term is saturation. So the number of water vapor molecules returning to the surface balances the number leaving. So in this case, it's talking about an air mass holding the maximum amount of water vapor content, and when it can't hold no more water vapor, it is saturated. So the air mass is saturated of water vapor. There are three ways that meteorologists measure humidity in the air. we have the mixing ratio, which is the mass of water vapor in a unit of air compared to the remaining mass of dry air. We have relative humidity, which expresses how close the air is to being saturated. So we will be working with relative humidity calculations on this lab. And we also have dew point temperature, so temperature at which saturation occurs. So for our next slide, we'll be covering how to calculate relative humidity. So for relative humidity, there are two main variables. The first one is specific humidity, which is based on the actual amount of water vapor in an air mass. The next one is maximum water vapor content. So the maximum water vapor content is how much water can an air mass hold? And the amount of water vapor an air mass can hold is based on temperature. So a warmer air mass can hold a large amount of water vapor content, whereas a cooler air mass can hold a small amount of water vapor content. And we can see that here in our chart. On the left side of our table, we have the temperature in degrees Celsius, and in the right side of the table, we have maximum water vapor content, grams of water vapor per kilograms of air. This is what that stands for. So as we can see here, the cool temperatures such as negative 40 degrees Celsius, they can only hold 0.1 grams of water vapor. And whereas if the air mass is 40 degrees Celsius, it can hold 47 grams of water vapor content. So that is one way to look at this table, the temperature of an air mass and what's the maximum of water vapor it can hold. So I wanted to do an example question. Just before sunrise, the temperature is 15 degrees Celsius with a specific humidity of 8.5 grams of water vapor per kilograms of air. Using the table, calculate the relative humidity. So first, to do this calculation, we need to know our specific humidity, and in this case, our specific humidity is 8.5. So I put here relative humidity equals 8.5. And to find our maximum water vapor content, I looked at our table and I went to 15 degrees Celsius. In this case, our maximum water vapor content is 10 at 15 degrees Celsius. I put relative humidity equals 8.5 divided by 10 times 100. And with this equation, the relative humidity is 85%. So our relative humidity is not 100%, so our air mass is not completely saturated. Well, it's not saturated at all, actually. But when our relative humidity is 100%, this is when the water vapor transforms into water droplets, and this is when clouds start to form or fog starts to form in the sky. When the temperature reaches 100% relative humidity, this is known as dew point temperature. So in this case, in an example question, what is the dew point temperature for 5 grams of water vapor per kilogram of air, you would go to your chart and you'd go to 5 grams of water vapor, and your dew point temperature is 5 because this is when relative humidity is 100%, because it can only hold this much. And the temperature is what is the function of it being the dew point temperature. So another rule is an increase in air temperature causes a decrease in relative humidity. A decrease in air temperature causes an increase in relative humidity, meaning that in the morning there is a higher chance of relative humidity being 100% because it's really cold when you go outside. And then oftentimes in the morning, you could see that on the leaves of plants or trees, you can see that there's little dewdrops on them, and this is how you'll know that the relative humidity is 100%. compared to the afternoon where relative humidity is very low, so there's no chances of condensation forming. So that's what this means. And for our next slide, this is based on cloud development. So what are the different ways that clouds form? And here you can see that there are 4 major mechanisms on cloud formation. But before that, let's just read this generally on the development of clouds. So as an air mass rises, the less dense surrounding air gives room for the air mass to expand. As it expands, the temperature decreases. If an air mass rises and cools down to the dew point temperature, clouds begin to form. So as we know here, dew point temperature is when relative humidity is 100% and the air mass is saturated to form clouds. And so in this diagram, we are going to look at the 4 major mechanisms that force the air to rise and form cloud development. So for diagram A, this one's called convectional lifting, and the sun is warming up the surface of the earth, and so there's a warm surface, and then the heated air above it causes the air to rise because warm air rises, and this causes the clouds to develop. For diagram B, this is known as orographic lifting, and the air rises due to the mountain. So the mountain forces the air to rise, forming clouds and precipitation to occur on this side of the mountain. This is known as the windward side of the mountain, where there is heavy precipitation, whereas this side of the mountain is known as the leeward side. And when the air is forced upwards, it precipitates heavy, but as it gets on this side, it travels down, compresses, and it warms up, and there's no moisture due to that process. And that's why this process is known as the rain shadow effect, and this is where you would see deserts, because there's no moisture occurring on this side. It's all occurring on the windward side. The next one is convergent lifting, and this is when you see different directions of air coming together. Right here, they're crashing into one another, and it's forcing the air to rise, and cloud development is forming. And then diagram D, this is called frontal lifting, and as you can see here, this is representing a cold air mass, and this is a warm air mass. So there are 2 different temperatures, and they are going to crash into one another, but due to these different air masses, it's causing the warm, humid air to rise and form cloud development. So this is the concepts that you all will be working with in your lab. Please stop by office hours if you need help, and also sign up for the tutoring services and if you need any help. So thank you for watching.